What's happening, y'all? My name is Jeff Anderson. I am a full-time math instructor here at Foothill College. This presentation is actually the story of how two Foothill College students translated an idea into a viable commercial product. I'm going to pass the mic over to our co-presenters, Hayden, Seto, and Chris Sakurada. I'll warm up with Hayden. Hayden, would you say your name, your major, and what your intention was for this project? Take it away, Hayden.
Hey guys, my name is Hayden Seto, and I'm an electrical engineering major at San Francisco State University. I was a Foothill College student from 2016 to 2019, and my intentions for this project are to help reinforce and highlight the importance of applied learning experiences in STEM.
I can tell you from firsthand experience, Hayden, that's exactly what you did. You have changed my life and the life of my students. Before we jump into that story, let's pass it over to our other co-presenter, Chris Sakurada. Chris, would you say your name, major, and what you wanted out of this project? Take it away, Chris.
Hi, my name is Chris Sakurada, and I'm an electrical engineering major. I attended Foothill College from 2014 to 2019, and I chose to join this project to hopefully expand the opportunities that students have to connect the theoretical concepts that we learn in class to practical applications.
So the mission for this project was to supply every student in a physics, circuits, and linear algebra course with an electronic learning lab kit. These consist of a DC current and voltage source powered by a 9-volt battery, along with a breadboard, resistors, and a digital multimeter to take measurements.
And so where our involvement in the project started was at version 2, and version 0 and version 1 were kindly donated by senior electrical engineer Mike Sassnett. And so what we started with was a working prototype seen in version 1 and a circuit schematic that you see here. From there, we went into a series of meetings about the prototype, and we decided that we wanted the device to be low cost, user-friendly, and as small as possible. And so one of Jeff's ideas was that we could create a battery cap. So we would create a battery cap that would be a voltage or current source on top of a 9-volt battery. So the next step was component selection, and so we got a list of all the needed components and we checked to make sure that they were available, where we could get them as low cost as possible, and then we searched out the schematic symbol and the PCB footprint that you see on the right for our ECAD software.
So once we finalized the components, we moved to the ECAD process, electronic computer-aided design, and this allows us to take our drawn schematic and digitize it into a working electronic model. For this project, we use Altium for our ECAD package, and once we had our schematic and a basic board layout, we moved on to doing a prototype of the actual PCB. We had access to a desktop CNC mill, which, if you can imagine, is like a router or a Dremel that's computer controlled. And this let us cut a few boards to try different configurations of the connector, component placement, and just verify that the dimensions of the board were correct. We then moved back into Altium and did a formal board layout. As you can see in the bottom right, that is the 2-dimensional board layout, and then the 3-dimensional model of the board is seen on the left. From there, we went into manufacturing. So we found a manufacturer in China called JLC PCB. They were able to do the first 150 boards at a very low cost and relatively quickly. And once we got the first 150, Chris and I got together and gathered the components and soldered them all in and tested each board individually.
We were then ready for packaging, and we decided to use a process called potting. And so we took a plastic enclosure and placed the PCB inside it, and then filled that enclosure with epoxy and let it cure. And after that, we were ready for final deployment.
To say that you got these ready for deployment, Chris, is an understatement. You all created these beautiful circuits. Here they are. I think they created about 75 of the DC voltage sources with positive and negative, and then also 75 of the DC current sources. Both of these plug into a 9-volt battery, brand new circuits. These have never been created prior to this project. The DC current source is particularly innovative in the sense that this did not exist in this type of form prior to this project. These guys delivered 150 of these to me. I took them immediately. We also got a more advanced engineering team led by the master engineer behind this project, the guy that designed the original circuit, Mike Sassnet. And in fact, Mike Sassnet used what we learned on these to iterate and improve for a fourth iteration. Mike, would you mind talking about what you learned from these sources and what you did with them afterwards? Take it away, Mike.
What we learned from version 3 is that the packaging, the potting box and the potting material itself, doubled or more the cost to produce it. And so we had to back away from all of that nice packaging. And Jose Espina and I worked together, and I knew he was an experienced guy with, that would be able to keep cost in mind and design a circuit board. And I guessed that he had connections, and he certainly did. So he came up with version 4 and knew where to get it produced. David Liu and Sunnytech have been important to him in other projects. And so this was a very simple thing for him to do, and he did it quickly and last fall.
Yes, he did. Mike Sassnet, Jose Espina, and Sunnytech iterated the design that Chris and Hayden produced so that they could automate the manual labor portion of it. Then we at Foothill College took that next iteration P block and ordered 2,000 units for 4 separate classes. Specifically, we created this thing called an Electronics Learning Laboratory Kit. We did that for Math 2B, Engineering 11, Engineering 37, and Physics 4B. The picture that you see on screen is actually the kit that we created for the Math 2B and Engineering 11 laboratories. Once we had those circuits in hand in winter 2021, we've actually implemented this in, 7 different classes affecting 163 different students. So students were able to, during COVID, drive to the library, pick up these lab kits, which fit into a Ziploc bag, drive them home, and do all of their lab equipment on a kitchen table with no fear of dying, no special training, and for a cost that is actually affordable. Previous to this project, in order to get a voltage source, you had to have a bench power supply, which is somewhere between $50 and $500. I'm really proud that the cost per unit was, what was it, Chris, like
$450. It was probably in between $4 and $450 was the ultimate.
Yeah, so Mike and Jose and Sunnytech, I think their cost was like $6 per unit. So we actually underbid them, but you all gave like hundreds of hours of labor. That's an order of magnitude saving. So instead of $50 or $500, it's only $5 per unit. And it allows students during COVID, this has been amazing because it means that instead of having to do virtual learning, you could do actual real world measurements, which wasn't possible before this.
Yeah, I think we spend so much time, we'll use the example of, circuits class. You spend so much time working on the theory and trusting like Ohm's law and KVL, Kirchhoff's laws, and you use them in your written tests, and then you get maybe 3 hours once a week in lab to go try and prove it to yourself. But you're also competing with multiple lab partners for time, and I think that with these P-block kits, you have the ability to do it on your own terms. So it's cool that, like you said, you could be at your kitchen counter doing your lab or verifying something for yourself, or you don't even need electricity. And in that sense, all the theoretical work that you do is now you have a place to store it by proving like with a applied experience like this, it's easier to organize that information and I think use it and have a better understanding of it long term.
But I just want to thank both of you for your contributions and to put it on the record that this was the early stages of this were kind of a community-based design process led by a master engineer and 2 Foothill students. So thank you both.
Well, thank you. Thank you and Mike. It's been a great experience. It's been some of the pieces that we put together of where we were at the time and what it really allowed to us to see the importance of like having an applied learning experience like this. Thank you.
We really appreciated the opportunity. Thank you.